Nice.
Hello,
Hello.
can you guys hear me?
Yep.
Yes.
Yeah, put on your video so I can see who is here. Welcome to our class, Lab in Machon, in computer architecture. You guys are Shana Aleph?
Yep.
Great. Leonard, can you put on your, and Avi, can you put on your video?
I'm working on a desktop right now. My camera broke. I'm waiting for a new one.
Who is that?
It's Avi Pincus.
Uh-huh. Okay.
Hopefully next week I'll have it.
Okay, great. Penny, yeah, okay. So I only, wait, so how many are you guys? Just a second.
Our other class finished like a minute or two late, so it might have taken people a little bit time to
Okay,
transfer.
all right. So I count 9, we're actually should be 14. Okay, let me share my screen with you. Yeah, I'll just share my whole screen. This is the Moodle for the course. You can find me English Lab with Nachum Danzig. And I actually have the whole class recorded because I taught it last year. And last year was also Zoom time. So here you see video. I have that twice. Wait a second. No, okay, I have it once. So here is a video guide to installing MIPS simulator and intro to the lab 1. So this will tell you how to install the program you need to use in this class. This is another useful link. This is all the commands that you have to know, that you have to use. You don't have to know them by heart, but you have to know how to use them. This is the link that we had just now to start our class. And these are my slides for the lab. It's actually the same slides for the course, at least the first section. So you guys are all in the course with me also. So we'll use those. So we'll start with that now. This is a guide. These are guides to the labs in the sense that I have the problem sets down here. Lab 1 problem set. There are 6 lab problem sets. That means now they obviously start off very easy and get harder and harder. Of course, your skills will improve. So it might take you equal amount of time to the first one as to the last one, but the last one is a lot harder. So you might want to pace yourself. I'll try to give you enough time to hand them in, but you might want to hand them in early. And basically as soon as you finish all the labs, you're done. And we're not going to have like we'll have some classes, and then now I'll teach you. But the truth is, these guides are all you need. I explain exactly what you have to do in each lab, but I even start doing the homework. So I even do, like for the first one, I do like about half of it. And even the second one, I do about half. A lot of them, I do about half of the work for you. I explain what you're supposed to do, and then I start doing it. And that's a good guide. But first, I got to talk about what the course is at all. So, let's start with these slides. And wait a second. Yeah. Okay, so like I said, these are the same slides that I use for the lecture, but in the beginning, because in the beginning, to get started, it's the same information. So first of all, rules for the lab. I'm not going to show you how to do the targeting. Actually, I do. This was written before we started doing these remote classes. When it's remote class, as a benefit to you, I start doing the Targilin because I can't go around so easily and help you with your problems. You should not copy. You can work in a team though, but both people in the team should understand what they hand in. Actually, I'm not going to have a defense. I'm not going to ask you to explain your work, but I should see that each team is different. The way they do their work should be different from each other team. Yeah, some of these rules are not true. Actually, I will be accepting the work through Moodle. Originally, we didn't do it through Moodle, but because we're in Zoom, you'll submit your work through Moodle. And I will grade you. Well, like I said, if we continue with Zoom for the whole semester, then I'll just grade you on what I see in front of me. But normally I would ask you questions. And if I see that it doesn't seem to me you understand what you did, I may give you an additional homework. All right, the truth is you should think about edge cases. If there are edge cases, means cases where, your program works for most numbers. Let's say I want to find, the square root of a number. Or square root is too hard, but let's say I want to find something mathematical about a number, and it works for most numbers, but not for all numbers. So those are edge cases. Edge cases are like strange cases that your program might not think, you might not have thought about, you might not have dealt with, like division by 0, or, if I ask you to find the, what's 0 squared? Isn't 0 squared 1? 0 squared is 1. Isn't that right?
0?
What? Oh, 0 squared is 0. You're right. What's 1? What am I thinking is 1?
0 to the 0.
Factorial. Is that right? 1 factorial. 0 factorial is 1? Something like that. I don't know. It's something like that. Now my math is escaping me, but we'll see. Rules for doing lab work. There'll be deadlines. I'll take off 10 points if you hand in late. You can only submit your work once. If I take off because you didn't handle something, you can't say, well, let me do it again and fix it. But you can ask me, I handled this in this case. I mean, don't ask me, please read my program and tell me if there are any mistakes. That I'm not going to do. That's called grading your homework. But you can say, I handled the case of this and this and this. My program works for this and this. Did I miss anything? And I can say, yes, it's still one more case if you think about it. Attendance is mandatory. Someone who misses more than 2 classes may receive a 0 in the lab. If you miss because of extenuating circumstances like you're sick, well, you should still get a 0 because that's why you're allowed to miss 2 labs, because those 2 times you were sick. It's not because you were playing basketball with your friends that you're allowed to miss 2 times. You're allowed to miss 2 times because you're sick. You're not allowed to miss any times except because you're sick. So that's why you can miss 2 times. But I may give you extra work to substitute for the fact that you missed more than that classes. And then I write, well, don't expect to do all the work during the lab, although you can use the lab time to do the work. The lab grade is based 100% on the lab work and attendance. And like I say, a solution which solves the problem mostly, but not in all cases, will get a grade between 50 and 80, depending on how many of the cases are handled. People who do not hand in the assignments on time and then try to hand them in all at the end will find this not possible because of time constraints. Okay, these are just some of the rules. You can go over them again on your own time. Okay, what we're going to do in this lab, first of all, since we didn't have the lecture yet, so let me a little bit say something about computer architecture. Well, can anybody tell me? Yeah, actually, let me ask you. Can somebody tell me what you think a class in computer architecture should teach you?
How to build a computer?
Say that more clearly.
How to build a computer?
How to build a computer. What do you mean by that? Build, like how to put a hard drive to get into a computer and how to get a motherboard?
I mean the software.
You mean the what?
The software.
The software? There's no software in a computer. A computer is 100% hardware.
Oh, so I don't know if that means yeah, the computer or I don't know.
Okay, well, you're right. It could be to how to build physically, how to put a computer together. Any other?
How a computer handles instructions that it's given.
How a computer handles instructions that it's given. What are instructions that it's given? I mean, you're correct. That is correct. How a computer handles instructions that it's given. How a computer gets the job done. In other words, if I want to add two numbers together, that's like one of the most basic primitive things a computer can do. It computes numbers. It takes one and produces two. How exactly does it do it? So in that sense, this course is a continuation of the course in logic circuits that you did, right? You did a course, numeric systems.
Yeah.
So in this course, we're going to assume that you know how to build a full adder. I'm not going to test you on that, but you understand what a full adder does. And so you already know that. Now the thing is to take some of those things that you've learned, like a full adder, a multiplexer, what other things did you learn? What other, can anybody throw me out another piece of hardware that you learned how to make?
An encoder.
A decoder, there you go. How to put all those pieces together and create a computer that can do not just addition and subtraction, but can do loops, do jump, we call it in this course, we'll call it jumps, can repeat the same code, can store data, can make an array, can do all the things that a computer has to do. And all of these decoders and flip-flops also, and all this stuff are put together in something we call the processor, the computer processor. So when you buy a computer, let's say it comes with, it says Intel Core i7 9th generation inside. That's the processor that you have. And each processor has its own architecture, its own design. So when we talk about computer architecture, we're talking about the design of the chip, of the processor in your computer, how it was built. Now, of course, the processor is, fits on the end, it's the size of your thumbnail, but inside it are lots of wires. Just a minute, I want to move my location. Okay, any questions at that point? So that's what we're going to learn. Well, this course is a continuation of actually what you did in semester one. It's a continuation of numeric systems, I think is what it's called, and it's a continuation of introduction to programming, because we're going to see how the two combine. How when I program something in C++, how that is run, how that gets executed in the processor of my computer. So the language that so you may have heard this, but a computer that you know this from your other courses, that a computer only understands ones and zeros. Does anybody know how it stores ones and zeros? I mean, it stores it in a flip-flop, but what's the role of electricity in all of this?
It's whether current can pass through or not.
Right, that's right. That's a flip, but how do we represent a 1 and how do we represent a 0? What's the difference between them? So this is an important point. 0 is essentially like a lack of current, like 0 volts. It's not really 0 volts. It's really a range of volts, 0 to like a half a volt. And then 1 is represented as like, 1.5 volts till 2.5 volts. That's the way a computer represents ones and zeros. And there's a gap in between. Notice I said 0 to a half a volt and then 1.5. So between a half a volt and 1.5 volt is indeterminate. In other words, it's not supposed to be there. That's sort of a safeguard to make sure that we're really one. You know, if there would be a tight border, a tight edge, then theoretically I could have like exactly a half a volt and I wouldn't know if it's 0 or 1. So therefore, a half a volt, even even a little bit more, 0.6 volts, will still be considered 0. Until, you know, basically it's supposed to be close to 0.5. I mean, it depends on the chip, but I'm just giving you an example. So voltage or lack of voltage, or theoretically, you could have a computer that would be ternary, that would have 0, 1, and 2. How would you do that? Can anybody tell me? How would you make a computer that wouldn't be binary, but would be ternary?
Ranges of voltages.
Right. You could just have ranges of voltages. You could have this range is 0, this range is 1, this range is 2. You keep going. What's wrong with that solution? I mean, why don't we do that? We could do it. Could be built.
It's really inefficient
Why?
because I think it would generate a lot more heat because you would need a lot of resistors in order to control the voltage that carefully, and then B, the more range, I guess, the more ranges you have of voltages, then the more there is a possibility of error.
Yeah, okay, I agree with both things you said. And there's a third, yeah, I mean, and also it uses more electricity, right? You're gonna have, I mean, you're not gonna be able to have tight ranges. You're not gonna be able to have like 0.0 volt, 0.01, volt, 0.02 volt, you're gonna have to have ranges with gaps in them. So you're gonna end up having a lot of volts. So we wanna keep the voltage down, keep the computer safer, and use less electricity, less power, and keep the heat down. You're right. When things start getting hot, there's more chance of electrical interference between the wires, the greater voltages. There's lots of reasons. Anyway, it could be done. Just understand that. Okay, so maybe I'll go back to my slides. We'll stick to my slides and go in the order. So I asked the question. So in the lab, we're interested in machine yeah, Misha, you can't come in here right now. Okay, so the language that the hardware, that the chip understands, is called assembly language. And it's also called machine language. The machine or chip is hardwired to understand one set of instructions. So actually, this is called the machine language or chipset. In other words, an Intel chip has a certain set of instructions that it can understand. An AMD chip has a different set of instructions. We're going to learn a third chip called MIPS, MIPS. It has its own set of instructions. They're all different. All the chips, when you design a piece of hardware, a processor, you implicitly design what commands it understands. You build it to understand. It does things when certain commands are executed on it. So that's the architecture. If I would write in machine language, I would write 1 1 0 0 1 0, I'd write in that kind of a language. But that we don't like to write in that because that's hard to remember the commands. So an assembly language is a translation of these binary commands into more human or English form. So in other words, this first one might be add and the second one might be subtract. So we actually just call it add and subtract. But actually, it gets translated by an assembler into machine language. Now, there's a one-to-one correspondence between an assembly command and a machine command. Each command in assembly goes to one machine command, as opposed to C++, where one command in C++ might go to 5 assembly commands. Now, when were assembly languages first invented? So there's a little bit of history of computers. The first computers were not programmable at all. What does that mean? For example, a handheld calculator, well, a simple one, is not programmable, which means you press the plus button and it does plus. You press the minus, it does the minus. It just does what you tell it to do on the keypad. It doesn't, it has built-in operations, but you can't make it do something that there's no button for. That's the way the first computers were. You want a program, you want to find pi to its, 25th decimal place. So you'll build a computer that's specially built to do that. That was the way it was originally done. No programming. You just build a new piece of hardware to do what you want to do. You want to run bank statements in a bank. You want to organize things in a bank, all the money and everything. So you know what you want ahead of time. You just build the hardware that does that. You don't need a programmer. You just build it. If you're an electronics major, you say, who needs programmers? Just build it. So the first programmable computers were came around 1944. Now we're still programming in machine language, which means ones and zeros. So in 1944, there was something called the automatic sequence controlled calculator, also called Mark I. That's what it was called. That Harvard had one of them, and it was used actually in the Manhattan Project. And it was an electromechanical computer, means it also had mechanical moving parts, but it was programmable. But again, with ones and zeros. There was another one in 46. By the way, you see that in the war, they needed these things. Why do you need a computer in a war? Well, you need to keep track of soldiers, but you also need to calculate trajectories of missiles and things like that. Now, there was a computer called EDSAC, Electronic Delay Storage Automatic Calculator, which had an assembler called Initial Orders, featuring one-letter mnemonics. Well, in other words, mnemonics means in other words, if you wanted to add, you'd write A. If you wanted to subtract, you write S. Now, what happened was like this. So what was the idea of assembly language? The idea was, well, there was this lady named Grace Hopper. You can actually find her on YouTube. She's not alive anymore, but she was interviewed by like 60 Minutes. They call her Amazing Grace Hopper because she did an amazing thing, which was she developed an assembly compiler for the Harvard Mark I computer we talked about. So what happened was she was a math professor in some university in America, and World War II started. And as a patriotic person, she joined the Navy, and the Navy put her into the computer division because she was a math professor. And she came there and she saw all the male programmers writing ones and zeros. And she said, this is silly. Write it in English and then just translate it into ones and zeros for the computer. And they said, well, that's too hard. We don't need, and we know we're used to doing these ones and zeros. And it's too hard. We don't want to. Who's going to write such a program? How are you going to translate it? You're going to have to write a program to translate the ones, the English code into the ones and zeros. So she said, I'll write this program. So they said, really? Okay, bavakasha, you want to do it? So she wrote the first assembler, and she basically speeded up all the work of all these people. Now they could just write in English what they wanted to do, and it would get compiled into machine code. Notice that I wrote first operating systems were until 1956. And I also wrote in 52, Grace Hopper also wrote the first compiler. Now, what is the difference between, you've probably heard that C++ is a high-level language. What does it mean, high-level language? It means you have to be very sophisticated to use it? What is it? What exactly is it that it's high-level language? Why is it? Anyone know?
Level of abstraction over the resulting binary.
Right, the level of abstraction, exactly. So what does that mean? That means we still have a problem, because as long as we have an assembler, we still have to write, there might, like a certain computer may have a certain function that, let's say, adds 2 numbers. And it also may have another function that adds 3 numbers together, because somebody wrote that. Some function that, some command, some instruction that is automatically hardwired take three numbers and put them together and add them together. So I have to call it add. I have to have two terms for it. Add one, add two and add three. I have to name the commands in English. And when I write add three, it knows to do that one. And if I write add two, but if I take that assembly and go to a different computer that only doesn't have add three, it only has add two, well, the names aren't right. And then the command might be different. The numbers, the ones and zeros, might be different on different machines. But also the assembly won't work. Even the English language code won't work because there may not be those commands on this other machine. Every machine has its own commands. So each hardware will have its own assembly language. So if somebody tells you I learned assembly, that you should ask him, well, which assembly? Assembly for an Intel, assembly for AMD? There's no one assembly. Now they're similar. Obviously, everybody's going to have a function, a command, an instruction called add, because every computer is going to have add. But some of them may have special commands. So our language that we are using is still tied into the hardware. And a guy who's a programmer on one machine may have a difficult time learning to program on a different machine. So the idea of a high-level language is to have a language that is what I wrote here is machine independent. C++ is a machine independent language. That's why it's called a high-level language, because I write this C++, and as long as I have a compiler which can turn it into binary for a particular machine, then I can just write in C++ my whole life. I can write, and if they come up with a new machine, as long as somebody writes a compiler that will compile my C++ code into that machine language, then I don't have to learn anything new. And not only that, I don't have to write any new code. My old program from 10 years ago will still work, even though the architecture changed. Right? My old C++ program will run today on an AMD architecture and on an Intel architecture. But I have to have a compiler. There's a different compiler for an AMD and for an Intel chip. In other words, right? You understand that? If I'm running a C++ program on an AMD machine, the compiler will have to be aware. I could write a compiler that can check which machine it is and then compile it differently for two different machines. So I can think of it as one program, but essentially that program contains two compilers, one for AMD and one for Intel. And so I install it on my computer, and I may have extra code that I'll never use because it's just designed for if I had installed it on an AMD computer. But understand that a compiler compiles specifically to a particular machine, and that allows for the abstraction that I can write in a language which is machine independent. And that concept is also the fruit of the mind of Grace Hopper. In other words, she also came up with that idea.
Wait, so AMD and Intel basically handle the instructions differently? Like they have different ways of like handling instructions that it's given or something?
Yes, they have different ways.
And specifically AMD, doesn't AMD license the x86 instruction set from Intel?
It may be. That may be. I'm not speaking. I'm just saying. I'm not choosing AMD. Maybe AMD uses the same instruction set. Possibly.
Wait, what's the point of it being different? Is one more like efficient than the other?
AMD and Intel use the same architecture, but like ARM, for instance, uses like a different architecture that's less powerful but much more power efficient. So like pretty much anyone that has a phone, you're using an ARM processor in your phone.
Okay, and there's RISC. There's also anyway. There are so AMD maybe have been a bad example, but my point is still true that different architectures require different assemblers.
So
we're
I
not
guess
actually.
is like AMD more efficient than Intel, or is Intel more efficient than AMD? Like what's
They're the exact same architecture, AMD and Intel.
So roughly, right.
They're just different producers of chipsets, but it's the same chipset.
So again, I'm not sure if it's they license the architecture or just the instruction set.
They're both x86, both AMD and Intel. Yeah.
Okay.
But ARM is like the main. There are basically only, I guess, like 3 real producers of chipsets. So AMD and Intel are using the same architecture. ARM is like the primary other architecture, and it's used in mobile devices primarily.
Well, there's a lot more than that. We're going to learn MIPS, which is a different chipset, and there's also RISC-V. For embedded devices, also for like, your washing machine may have a chips. There may be a computer. There is a computer in every washing machine. It's not going to be an Intel. It's not going to be the x86 architecture, and you can program it. So there's lots of chipsets, but you're talking about practically as a purchaser of normal of a phone or a laptop or a computer. So I don't. You're probably right there. Wait, can you put Raphael? Can people put their videos on?
I don't have a camera. I'm on a desktop.
For people who do, I don't think. Yeah. Okay.
Is
So-
there a grade requirement to have a camera on?
Well, I'm not going to count you as being here if your camera's not on.
Wait, you don't. We
but
actually lose
attendance is
attendance if our
required.
camera isn't on.
Say again.
We lose attendance if our camera isn't on.
Unless you have a good reason.
Does not having a camera count as a good reason?
Yeah, that's a good reason. But yeah. Yes. Okay. So wait a second. Characteristics of assembly. Is that where I am? Yeah. Okay. So there's an extremely small set of commands that the chip can understand. From these small commands, you build your program. The assembler translates your human assembly commands to machine code. Okay. Now I thought, like, you guys are going to say, well, I know C++, why should I learn assembly? So I thought of some reasons why you should learn assembly. It gives you complete control over the final machine code. In other words, high-level languages are also compiled to machine code, but they will contain a lot of inefficient code. So that you can see sometimes. As I write, let's say, I might a loop, int I equals 0 as long as I is less than 10, I plus plus, and I do something in my loop. It's gonna, if I would write it in assembly, I could probably do it in in eight lines, and if the compiler writes it in assembly, it might be 16 lines. So if I write directly in assembly, I would actually be able to get the code to run faster, which might be important if I'm doing something like high frequency trading on the stock exchange, and I want to do stuff extremely fast. And every fraction of a second that I can do trading faster, I can make more money. So it would be useful to write in assembly. Or if I'm writing in it for something in an extremely small space, I want to write, I want to get the smallest possible memory in my washing machine, because I want to sell the washing machine for as cheap as possible, and nobody cares how much memory is in the computer there. So I would like to use as little as possible so that it's cheaper. So I might write it in assembly. And also, to be professional, you need to understand the underlying working of your program. In other words, it's very well and nice to just program in C++, or in Java, but you should know what your program is actually doing in reality. Okay, so we're going to learn MIPS, the MIPS instruction set. So MIPS stands for microprocessor without interlocked pipeline stages. It's a reduced instruction set computer, which is what I called RISC, but it's not RISC-V. It's a different RISC. Now, what does it mean, reduced instruction set? It means it won't have a command like add 3 numbers together. You want to add 3 numbers together, first add 2 and then add 1 more. In other words, it won't have lots of specialized commands. That means reduced instruction set. It doesn't have every possible thing you could ever think of, but it has basic things that you can get things done with. Now, MIPS was used in the Mobileye application which was used in the Tesla, in Model S. I don't know if that still exists, but there I gave a list of some things. I did a search and I tried to find what is using MIPS. These are some of the things I came up with. So it's actually a chip that's still widely in use in embedded systems. In other words, in your car, when it wants to detect if there's a pedestrian there and needs to press on the brake, so it'll use, there's a chip there that's detecting those things. We will program on a simulator called Mars, designed to be used with the textbook Computer Organization and designed by Patterson Hennessy, which is the official book of the class. You don't need to buy it, but that is the official book of the class. Actually, I'm not, wait, am I giving you the lecture? I'm not giving you the lecture, right? Avi Treisman is.
Treisman, yeah.
So he's giving, if you had lectures with him?
Yeah, we had to.
Oh, you had to, great. So he's giving you the slides from that book, I believe. Okay. So what did I say? So we have this Mars simulator. Why do I have, and can anybody tell me why we have a simulator?
Because we don't have the
Because
actual
our
chip.
chips don't run MIPS.
Right, because if we would take our regular MIPS commands and try to run them on our Intel or AMD, they won't work. We have to have a MIPS chip. So we'd have to somehow buy a MIPS chip. So instead of buying one, we have a simulator, which will run as though we had one. It'll run our commands. So let's get to the language. So we have in C++, we might do something like this. A equals, did Avi go over these examples?
I don't think so.
No? Okay. Because these are actually in the book. For example, in C++, I might write A equals B plus C. I hope everybody knows what that means. In assembly, in MIPS assembly, it'll look like this. Add A, B, C. So obviously B and C are added and put into A. And subtract B, D, A, E. So there you go. You already know two commands in assembly of MIPS.
We had this in class. Just a quick question. Can we do add A, which will add A plus A and store it into A? Or we have to like
Yes.
put it into a...
You could have A, and then it would take whatever value A had, add it to A, and put it in A. So you had this example also. This, well, I'll just do it quickly. If I want to do something like this, one line in C++, it'll be 3 lines in assembly. That's just what I was telling you, that it could be longer in assembly in a sense, but the compiler will turn this into this. Again, the compiler will turn this into this. Now, this is not exactly accurate, what I have here, because actually, this is also not accurate. Actually, we'll see in a minute. You can't have A, B, and C, really. But this is just to give you the general idea. So how am I going to do this parentheses? There's no parentheses in assembly. So how do I do it? I say take G and H, add them together, put them into a variable called T0. Take I and J, put them into a temporary variable. That's why it's actually T for temporary. And I and J, put them together and put them into temporary variable T1. And now that I have this and this stored, I can subtract G, and I can take G, subtract this minus this. So subtract this from T0. So T0, I'm removing IJ from GH, which is T0. And I store it in F. So you see that you'll have to write longer code. Did you talk about registers with Avi?
Yeah.
So what's a register?
It's like the memory storage that's used by these languages.
Yes. A register, what is it physically?
A piece of memory.
Yeah, how would you build it?
You would set a slot in memory to like whatever the variable you want to put in there.
No, but what is it made out of from your course in digital systems?
Transistor. Made out of a bunch of flip-flops.
Right, a bunch of flip-flops. You take a bunch of flip-flops, 32 of them probably, and you can store a 32-bit register. A register is very fast. In other words, the time it takes to put a number into it, take a number out of it, is quick. So it's 32 bits long, which is also 4 bytes. A byte is how long?
8 bits.
8 bits.
8 bits. So 4 of them is 32 bits. What's the largest value that could be stored in 32 bits?
Due to the power of 32.
Say it again, 2 to the power of 32 minus 1. That would be the largest value. And if we wanted, that would be if we only stored, if we didn't store negative numbers. If we wanted to have a range of positive and negative numbers, we'd have to use half of them for positive, half of them for negative. So it would be, instead of 2 to the 31 would be the largest value. Okay. Commands. Every command must also fit into 32 bits. So, okay, fine. That's an important point. I have a whole slide for that. But I assume Avi talked about that. Is that true?
Not sure. Could we go over that, please?
I don't think we discussed like the relationship between the commands and the register, just that registers existed and they are the memory storage.
So a command, well, we'll get into it in more detail, but I'll just give you an example. What's a command or an instruction? An instruction is add this to this, to add these three, add this and this and put them in, add G and H and put them in T0. That's an instruction. The zeros and the ones that represent this command, remember, every assembly command is translated into zeros and ones. So the zeros and ones that represent this, it can't be longer than 32 zeros and ones. In other words, I can't have more. Every command must fit into a register. This is because remember, the program itself is stored in memory and must be put into a register when I want to run the command.
So does that mean a system with 32 registers only actually has 31 usable registers for any given command?
No, because the commands is a special register for storing the command, which is not part of the 32. Using registers, so now we're going to do that same program that we did before, except I'm going to use it registers, because the A, B, and C was actually illegal. I can't do that. I have to only use registers, and the registers have a fixed set of names like T0, S0, S1. Those are registers. You can't just make up names here. I can't have like, Q0. There's no register. W0. There's just T and S for now. We'll learn a few more.
How would you define them though?
Well, what this is a reference to an actual location on the chip. In other words, there's 32 flip-flops built next to each other, and they're glued onto, the chip, and that's register 1. You know what? Let me do something in a second. Wait, here, you guys see what I'm running now? You see this?
Yeah.
Yeah. So if you look over here, these are the registers. It says register. The name of the register, and here they are. And for example, the first one is 0, the second one is AT, the next one is V0, V1, A0, A1, A2, A3, T0, T1, T2, 3, up until T7, then S0. These are the names of the registers, and there's 32 of them. They also have numbers. The numbers are just, if I want to, I can refer instead of calling it T0, I can call it register 8. Because there's 32 registers, and they have numerical names, and they also have linguistic, letter names. And that's like the variables in my program, similar to variables. And that's where I can store numbers. What actual number do I want to store in this variable? Well, whatever I want, but whatever I do store in it will be written in this column, value. So at the moment, when I turn on the computer, they're all 0, except for some of these ones down here, but they're basically all 0.
So every single variable has like a different type basically that you can't change?
Not a type. Why'd you say type?
No, because while you were going through like the things, it was like some of them it says temporary value not held throughout the thing, and then it.
Oh yeah, there's a reason for the names. Like the T, temporary, not the names are just convention. I'll
The
explain that
teacher
later.
spoke about this in class, that the T is conventionally used for temporary, to save numbers temporarily, and the S are more to store our data variables.
That's correct, but yes, that is correct. This, by convention, he means that programmers across the world agreed to work in this way, but you don't have to. These are all open to your use, and there's no type in this language here. Let me just do something. Okay. Okay, so I just wrote my first little program here. I don't know where to put these pictures, but yeah. Okay, so now I'm going to go like this. Compile, or I turn it into assembly. Notice, here's what I wrote. Add I T1, T04. It changed it into the numbers for those registers. See, T0 is 8, T1 is 9. So it wrote, instead of T1, it wrote $9, $9, and $8. That's like the translation of my assembly into a lower level assembly without the names into numbers. And then over here it says code. This is actually the ones and zeros that it got written into. It's not written in ones and zeros. It's written with, anyone knows what 0x means?
X.
Hexadecimal. Very important rule. Anytime you see 0x at the beginning of a number, it means the number is in hexadecimal, base 16. So we use base 16 because it's very easy to convert to binary, to and from base 16. Every number is 4 digits of binary. So I can just see 2, and I know that I write 0010. 1, I know I write 0001. So this is the ones and zeros of the code. And the address is where in the memory of the computer this resides, where it is actually written. It's written to memory location hexadecimal 400,000. Now, if I run it,
shouldn't it say range in the memory? It's held in from here to here.
That's where there's a range of where various lines could be held, but any particular line can only be in one specific location. That line
So
can't.
that address in memory is like a very high number.
Oh, because the range starts at 400,000, and it
The
goes.
range starts at 400,000. How do you know
Yes.
where it ends?
It ends at 10 million. I'll
No,
show
I'm
you.
saying
I have a
for
slide
that
right
line
now.
of code. I'm saying for that line of code.
Oh, this line of code, it ends for it's 32 digits of binary. And we said that 32 digits of binary is 4 bytes. So it ends at 400,003. It takes exactly 4 bytes of memory. It's in location 400,000, 400,001, 400,002, and 400,003. That's enough bytes to store one 32-bit instruction. Now, if I run it, now look, I want you to look very carefully over here. They're all zeros over here.
I have a question. Why is a 4 in the side of the add? It's a 4.
Oh, because this 4 here?
Yeah.
Because this command is add I. Add I is different from add. Add I means add an immediate value. An immediate value means the value is written into the command. If you notice, over here it says 0004. That actually refers to the 4 over here. These 16 bits, these 16 digits of hexadecimal represent the location of the value that I want to add. In order, I'm adding the number 4, not what's in register 4, but the value, the actual value 4. I'm adding it to register 8 and then storing it in register 9. Now register 8 is 0, because we saw all the registers are 0. So if I add 4 to 0, what do I get? 4. And then I store it in 9. I should see, after I run this program, in register 9, which is T1, I should see a 4 over here. Let's run.
It's not the same thing as just add.
Look, now there's a 4 in register 9 because I ran this program.
If I
Add
did,
I is very different now. If I would do add over here, it shouldn't work. I mean, the processor might be nice to you, but if I type add, it tells me add, register, register, register. Actually, it does show me with a number here, another option, but that's not really true. That's pseudocode. This simulator will let me do that, but in reality, it's illegal to do that. So I'm not going to use these versions. I'm only going to use the first one that shows up. So if I would write
add, you can only add registers. You can't
exactly.
add numbers.
So if I would do, like, for example, $T1, $T2, $T3, and run that, well, it wouldn't do much because it would just add 0 to 0 and put it in another register. So it'd be 0, but it was 0 before. I can't get started. How do I get my first number into a register? So I have to use add I, and then I don't write immediate. I don't write a register. I write an actual number. So if I write 100 and I write it, now I'm going to see in register T1 100.
Does the integer always have to be the last?
Yes, it does. Yes, it does. Very good question. Look, if I do add I, it writes, oh, remember, only use the first one. Never use any of the other instructions that are shown. They're all pseudocode. I don't allow pseudocode in the lab. So it says T1, T2, and then a number. It gives you an example, minus 100. That's the order, must be. Because the way the command works is it takes these two, adds them together, and puts it into the first one. The last number must be the immediate. So you see there are registers. My main point was just to show you that there are 32 registers. They're physical locations in memory. They're a kind of memory. They're a very fast memory. And they're a physical location where you can store numbers. Now this software you have to download on your own. I have instructions on how to do it, as I told you. Very important is that you first have Java on your laptop. I always get into this trouble where sometimes people don't have Java and then they download it, and then when they put Java later, somehow it doesn't find it. It doesn't work, and I don't never know how to solve that problem. But there is a solution. But in any case, you have to first have Java. What I mean by that is you need the Java virtual machine to be installed on your computer. And I tell you how to do that in my instructional video.
Does it need to be specifically Java 9 or can it be the most recent Java?
Oh, it probably could be the most recent Java. At the time I wrote the video, I mean, that was what I found.
Okay.
Okay, so here we have using registers. I'm assuming that G is in somehow the value of G is in the register S0, the value of H is in that register, the value of I, are these assuming values of G, H, I, and J are stored in S0, S1, S2, and S3. How exactly it gets there, I'll explain soon. But for the moment, assume that they're there. Then the translation of this line of C++ would be these 3 lines. Okay. Storing more data. So where do we keep static array data? What if I want to make an array? What about dynamic memory allocation like new? Obviously, 32 registers is not enough to store my arrays. My array could have thousands of pieces of data. So we store this in what is called the data segment. But I'll get to more on that. I'll explain that more in the next couple slides. All right, so now what do I say? Assume data is in the data segment. We can load it into one of our registers. All right, there is such a thing as the data segment. You can think of it as memory, computer memory. You buy a computer with 64 gigabytes of memory. So that's what I'm talking about. That 64 gigabytes of memory has some data in it. I want to copy it into a register. What am I going to have to do? Well, I have to do 3 things logically. I'm going to have to know where the data is, and I must specify where the data is. Where is it in the memory? I must specify where to copy it to. What I mean is which register do I want to put it into? And then I also have to say how many bytes do I want to copy? Because theoretically, I can copy just 1 byte from the location that I give it. Now, I'm going to give it the location of a particular byte, but it might want to copy that byte only, or it might want to copy that byte and the next 3 bytes, a whole word, 32 bits. So I have to tell it 3 things: how many bytes, where to copy it to, and where the data is. So here's an example. Know what I wrote in red. This example is not fully correct. So, but let's start with it. Let's say I do something like this in C++. This is actually referring to memory. If I say array, I have some array, and I want to go, I didn't explain how this, in this line of code, I do not discuss how this array got created, but assuming that this array got created, and assuming that there's something in location 8, I want to add it to what's in variable H, and I'm going to put it in G. So how do I do that? So for that, we need new commands. We will load a whole word, assuming that this is a word length variable. In other words, in C++, this is an important point. In C++, you have types like float and int and double, and long and bool. You have various types in C++. In assembly, we have no types. All we have is lengths. How many bytes long is this data? We just have data. We don't even know if it's letters, if it's characters, or numbers, or decimal numbers, or whole numbers. It's just data. But we want to know how long is it? Is it 1 byte? Is it 2 bytes? Is it 4 bytes? So I say, assuming we're loading a word, which means 4 bytes, 32 bits from the array into a 32-bit register, we'll do the following. We'll say, go to array, assuming that S3 is pointing at my array. And as S3 has the address of where the array is. The array is in memory space 10 million and 50. So S3 will be 10 million and 50, but I don't want the first one. I want the 8th one. So I write an 8 over here. Now, it's a little bit unusual to see that when you're a C++ programmer. You'd rather have the 8 inside the parentheses. But the other way around. Kachaze. That's just the way it is. So I have my array, and then I have the 8 to tell me go to the 8th place. And then I want, oh, I need to plug in my computer. Okay, so I want to load. You go, question?
Yeah, how many words can be saved in S3? Like you said, you do S3 and then you go to the 8th placement. So like, how many words can be saved under S3?
Well, S3 is just a register like any other register, but we're assuming that it has the address. In other words, here, let me show you. I better show. It has the address of where the array is. So, for example, here, add. Just a second. Add. Oh, I made a mistake. Here. If you look here, see it says data segment. So the data segment has addresses. They start at 10 million, 10,000. I said 10 million because that's the official place it's supposed to start, but on the simulator, it starts at 10 million, 10,000. At 10 million, 10,000 is where the data segment is. And it goes, and all of this is 10 million, 10,000. This is 10 million, 10,000 plus 4 and 4. This is 10 million, 10,000 and 8. This is 10 million, 10,000 and 20. Notice it's all empty. But this value, when I say S3 is pointing to the array, what I mean is the array is here. Like here's a number, here's a number, here's a number, here's a number. And S3 has the value 10,000, 10 million, 10,000 and 60. It has that value in it. That's not the value of the array. That's the location of the array. The value of the values of the array are what are at those locations, which starts at that location and then continues forward. In fact, you used to using the term index to talk about an array, index number 8. And I'm going to call it an offset instead of an index. And there's a reason for that. And it also helps explain something that was maybe perplexing to you in C++. It may have perplexed you that arrays start at 0 and not at 1. But there's a very good reason for that. Because if the array name, remember, you probably learned with your teacher that the name of an array is a pointer to the first element of the array. So the name of the array is 10,000, is pointing to the location 10,000, 10 million, 10,000 and 60 right here. At that location is a number, let's say 25. If I say, but if I take that same name, which is 10,000, 10 million, 10,000 and 60, and I add to it 4, or add to it whatever, 4 in this case, I'll be over here. And that'll be the next element in the array. So 0 basically means the 0 spaces from the beginning. 1 means 4 spaces from the beginning. 2 means 8 spaces from the beginning, depending on the type. If it's a char array, then 1 will mean 1 space from the beginning. 2 will mean 2 spaces from the beginning. Okay, so if you're asking how many can S3 store, it's just storing the location of the beginning of the array. The 8 is telling me how far to go away from that beginning, and then grab that number and put it into T0.
And how do you know you won't bump into like S4, which is the next spot in memory?
No, S4. No. I'm not going to S3. I'm going to the location that S3 has in it. Let me show you. Here, let me demonstrate. We will get to it if I wouldn't explain it, but let's say here, I'm going to make data. I'll make an array. Dot data. Dot text. Text is the actual code. Data is an array. So if I say like, okay. Now look, I want you to look. You see the 10 here? 11, 12, 13, 14. That's my array, 15. What's the location of this array? What's the location of this array? It's in a data segment at memory space 10,000, 10,000,000, 10,000. Is that clear? But what do you mean it's at that location? Only the first number is at that location. The second number is +4, like it says here. It's 10,000,000, 10,004. Because each of these is a word taking up 4 bytes. Now, if I look over here, if I run this program, and I look over here, look what I see at S3. Well, this number looks like nothing meaningful to me. I can change over here. I can say hexadecimal. Now I'll see it in hexadecimal, and it will be meaningful. S3 is here. What do I see there? Somebody?
Location 10,000,000, 10,000. Well, the number.
Exactly. S3 is 10,000,000, 10,000. Well, that happens to be this location. If S4 has nothing to do with it, if I do, when I say load word, going back to my example, so at location, wait a second. So when I go and I say load word at S3, but +8, I'm not saying go to S4 or go to S5. I'm saying go to the location that S3 is pointing to, 10,000,000, 10,000, add to it 8, and take the value that's there, which might be 12 or 13, whatever it was, and store that in T0. So if I would do that, let's do that. Let's go back. And I say, instead of this, I say load word into $T0. I want to store the 8th location from, let's try to get the 13. So let's write, this would be the 0, 1, 2, 3. So let's write 3. No. Let's try to get the 14. Let's write 4. And what do we give it? The beginning of the array, which is a pointer to the beginning of the array. The pointer, this goes back to C++ pointers. S3, a pointer is an address. So an address is a pointer. S3 is an address. So S3 is a pointer. Now,
Can I?
Question?
Yes. When you said in the data I don't know what to call it. My array automatically got placed in 10 million 10,000, and then when you load address to
Who's talking?
location S3 of my the on the chip, what's it called, the
Who's talking?
so you loaded my array by writing my array, you loaded the address to S3.
Yes, I didn't explain the LA command. What the LA does is it puts in to S3 the address of my array.
Okay, thanks. That's
As we saw in reality, that's what it did. So now I'm going to run this. And let's see what happens. What should be in T0 by the end of this?
14.
Zero.
It should be 14. Let's see if it is. I compiled it. Now I run it. Let's go over to what was it? T0? T0 is got B in it. B, let's change it from hexadecimal to regular values. B is 11, not 14. Why didn't it get 14? So the answer is like this. Since I declared this as a word, it's 4 bytes. Every digit here is 4 bytes. So if I write 4 here, I actually mean 4 from the beginning. 4 from the beginning is 11. 11 is 4 bytes later. Because that's what it says over here. 11 is plus 4. If I want the 13, I've got to write plus C.
Oh, because in a C++, whenever you do +1, I guess it basically does the 4 for you.
Exactly. In C++, if it's an integer, it multiplies your 1 by a 4 and turns it into 4. If you write 3, multiplies it by 4 and gets 12. If you write 7, it multiplies by 4 and gets 28. It multiplies by 4 because it's an integer. But if it would be a character array and you write 1, it's just going to multiply by 1. It's not going to do any multiplying.
Is there a way to write 4 and that means 4 words?
No.
Or you have to write.
You have to do the math in your head. If I want to get to 13, I'm going to have to say 16. And that should give me the 13.
It's in decimal. You don't write it in hexadecimal, right?
Well, here, look,
like
it
here
gave me
it's
14.
Here it's in hexadecimal.
I wrote 16. It gave what? I could write it in. Let's see if I can write it in hexadecimal. I'm not sure about that. You want to write in hexadecimal? So 0x 10 is 16.
I feel like after we learn this language, we'll appreciate how much C++ does for us.
Yeah, it's true. 14, look, the 14 worked. I can write it in hexadecimal if I want. I can write it in I can write it in decimal. But if I don't write 0x, then it's obviously decimal. But why did it give me 14? Because I did, well, let's put it back in. I prefer 6. So this is 0. This is 4, 8, 12, 16. So 16 is where 14 begins.
13 will give me a compilation error.
If I would type, well, first of all, if I want the 13, I'm going to have to write 12. True? If I write
No, that's not. I meant if you wrote.
If I wrote
number that fell in
13
the middle.
here, it will give me not a it'll give me an error. I don't know if it's a compilation error or a runtime error, but it'll give me an error because there's something called word boundaries. I can't load a word on something that's not a multiple of 4. Words always start at 0, 4, 8, 12, 16, 20. They always start at multiples of 4. 13 is not a multiple of 4, so I can't load a word starting at that location. So I have to grab it at the right boundary. All right, in the time we have left, let me go back to my slides just so that I can not miss anything. But you'll see that what we just did now is actually what I do in the slides. So So the 8 here is clear. Well, the 8 here is clearly wrong because if I wanted to do 8 in C++, what should I really write here?
32.
32, 8 times 4. So here I just explained that each byte has an address, not each word. You might think each word has an address, but each byte has an address. And that's why I have to jump to reference the first word. The second word is at offset 4. So really, I have to write like this, 32. 8 times 4 is 32. That's the way I have to write it.
It starts
Which
at
is
0, it's 28.
What?
It should be 7 times 4 because you started 0, 0.
No, 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 no.
Why? You want this?
Because 8 is really the 9th number, right?
Yeah. And you want the 8th number, don't you?
I want the 9th number. This is the 9th number. In
No,
C++,
the 8 is
if I write 8, remember, I'm translating literally, I'm translating what the C++ code is. If the C++ is 8, then it means the 9th number, because the first one is 0. We start at 0. So if I want, just think about it. If I want the 0th one, I'll write 0. If I want the first one, I'll write 4.
Yeah, got it.
So what is 4? 4 is 1 times 4. So if I want the 8th one, it's 8 times 4, 632.
Yeah.
Okay. Now, this is just a diagram that's very important to know. Basically, I already explained it to you. The program code starts at 400,000. We saw that. And it goes up to 100 to 10 million. Now, we saw in the simulator, it's not 10 million, it's 10 million, 10,000. Don't know why the simulator is not according to the rules. The official rule of the chip is like the way I'm showing you. And the memory ends at 7FFFF. That's the end of the memory. And this is called the stack, and this is called the heap, and we'll talk about it more later. But for now, you can think of all your arrays are going to start at 10,000, and that's why it says static data, and go up, 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 up. If theoretically they could go all the way up to here, then your stack would be very small. That's why there's arrows here. There's no, these lines are not fixed. There's no numbers here. This static data could actually be infinite, go all the way up to the end, and then the stack would be very small, and the heap would be also very small. These can move around, but it'll start. Your arrays will start here, and keep going one after the other. If I make 6 arrays, each one will be exactly after the next, or the previous. I mean.
Notice that the program code is it's limited to the space between what is that, 400,000 and 10 million.
Yes, which means you can only have approximately 10 million bytes in hex, 10 million hexadecimal bytes of code. Well, that's enough for you guys. That's a heck of a lot of space. That means 10 million lines of code, something like that, less. So we saw that. Locating bytes within words. The address of the word from the previous slide also refers to the leftmost byte of the word. If I want the next byte, from the left, then I add 1 to the address. I actually have a video about this big endian and little endian. I don't want to explain it now. I made a video for you. Just a second. Because it takes time to explain and you might want to go slowly. And it's not crucial for you to know. Oh, I lost my Moodle page. מעבדה במבנה המחשב. So, always a noise in here. Oh, I don't have it here. Maybe I only did in Hebrew. Here, if you do Hartzaot Shel Nachum Danzig, I also teach this course in Hebrew, and then I teach the lecture, like what Avi's doing. Where? Oh, well, I don't see. Oh, here, little endian or big endian. That might be in Hebrew. It's just a question of some chips look at they give the address of the rightmost byte, or some chips give the address of the leftmost byte. That's the in a nutshell. That's the concept. Doesn't really matter. The way if you understand what I explained about how the addresses work, that's all you need to know. No, this is the wrong slides. Oh, that's why I couldn't see. This is my, okay. So fine. Storing a word into memory. Yeah, Lena, Misha is here. I don't know how to get out of that. So now we're doing the same thing, just one next step. Up till now, what we did was we took this and we stored it into it. If you look at the difference in this example and that example, here, I just took an array and I put it into G, a register, which is, I mean, I did that with load word. Now I'm not going to put it into a register. I'm going to put it into another location in the array. Now that's one nice line in C++. Take it from one part of the array and put it into another part of the array. But in assembly, you're going to see you're going to have to do it in 3 steps, because what I'm going to have to do is first do this part, and that's the load word. Grab 32 space from the pointer S3 and put it into T0. Then I've got into T0, I got to add the H to it. Now, assuming that H is somehow magically in S2, then I add it to S2 and I store it in a temporary variable T0. And I can use T0 again because I'm no longer interested in it. Now, I don't mind destroying this value because I'm just going to copy it. So I put it into T0. And now I want to put it back into memory. I want to do the reverse action of load word. Load word took it from the data segment and put it into a register. I want to do from a register, that's what I'm doing here, into the data segment. So you could think just do load word again, but reverse it. Put the T0 over here and the other one over here. But that's not the way assembly works. It's a different instruction. It's the S word, the SW, store word. Store word, and then the order of the registers is the same. But it means if you have an arrow, here the arrow is pointing from the right-hand part to the left-hand part. Here the arrow is pointing from the left-hand part to the right-hand part. So I'm storing what value that I just put into T0, I'm storing it back into the array at location 48. Why location 48?
12 times 4.
12 times 4. I want to put it into location 12. So 12 times 4 is 48. I hope. Okay. And this we already saw. Adding a constant to a variable. Add I. 4. Put 4 into, this is I equals I plus 4. So I use the same register. S3 equals S3 plus 4. Notice I'm just using any register I want because these are just code segments. They're not actually a program. All right, now we have another topic which Avi, he didn't discuss this with you? Representing in MIPS instruction format?
We did it briefly.
You did it briefly. Really? Okay.
Like we looked at it. I don't know, maybe not briefly.
Maybe not briefly? Well, anyway,
Depends what he described briefly.
I'm going to stop here for today. The truth is, it's totally not necessary for you to do your work. We already learned load address to get the pointer to an array. And here's an example creating an array and accessing it. This is, I sort of did this with you. I create an array, I get the pointer, I load the 24th character, I do something to the 24th, I do something. Oh, here, you see the problem you're going to have with an array. The problem you're going to have with an array is, how do you go through the array? If I said you have to hard write 0, 4, a lot of people will be tempted to do something like this. Here, I'll show you. A lot of people are tempted to do something like this. $S1. And then S1, I'll do, you know, S1 equals S1 plus 4. And then I'll loop somehow. I'll loop, by the way, you can loop like this, jump. I'm going to do an unconditional loop. Jump, you know, start. And start is a label. We write a label here, start. And this jump means make a loop. This is an infinite loop. This will, you shouldn't do this because, don't try this at home because it will crash your, you know, your simulator will never finish. It's an infinite loop here. It means jump to the start, go up to line 5. Go down, go up to line 5. So here you see that S1 is going up by 4. Each time I'm loading a different part of the array because the variable S1 is over here. But guess what? Sorry, Charlie, this does not work. Sorry, guys, you cannot do this. This must be a number here. So how are you going to do it? The answer is with pointer arithmetic. Instead of writing S1, let's write S3. We'll keep our index always at 0, but the pointer will add 4 to it each time. So if originally it was pointing at 10,010,000, now it's going to point at 10,010,004, then 10,010,008. But so we're moving the pointer across, keeping the index always at the first thing it's pointing to. That's what you learned in C++, pointer arithmetic. Instead of accessing an array through its index, you access it with a dereference of a pointer, and then you just incremented the pointer. That's what we're doing over here. All right, guys, we'll stop here. You don't actually know enough to do the first lab because we didn't learn loops properly. This is not the kind of loop you're going to do. But what you can and should and must do is do the installing of the MIPS, of the Mars simulator. I have an instructional video on it. If you don't find the video, email me. My email that you should use to email me is this here, targilimdanzig@jct.ac. No, not JCT, at gmail.com. targilimdanzig@gmail.com. If you have trouble, if you don't find the video, put it that way, then I'll make sure the link is right. I think the link is right. But so that's your homework. Your homework is to install the simulator, be able to do what I'm doing here. All right, that's it for
email for. That's just your email.
That's my email. If you have a question or trouble, if you have trouble accessing the finding the link for the instructional video on how to install the Mars simulator. But if you have any question, you can email me.
I assume the first lab will be due after next week's lesson, then? I don't know how the due dates are.
I will, yes, next week's lesson. Next week, I will explain to you more and enough for you to start the lab. The truth is, anybody who wants to start doing work, bavakasha, you can, I have my instructional videos. The truth is, we don't need to ever meet. You have, my videos are sufficient for you to do everything you need to do. But I think we should meet. But but it's probably better for you probably what we're gonna do is you're gonna watch the videos and then we'll meet just for questions. Because, except for next week. Next week we'll meet again like this. But in general, that's what we'll do because I think it's a better learning method. Unless somebody disagrees, feel free to write me. But I think you'll watch the video and you'll see what to do. And if you have a question, then you can do it in class. But the videos are better because I talk very succinctly and short, and I explain exactly what you need to know to do each lab. So I don't waste your time, and you can watch the video, in parts if you want. So that's probably what we're going to do. You're welcome to write me if you have opinion about how we should run the class. If we go back to campus, well, we'll see about that. I don't think we will. Okay, guys, have a good night.
Have a good night. Thank you.
Sure.
Thank
you.